sorry, I cut you off, Bruce. Okay, so we're going to talk about double integrals in polar coordinates today. I'm going to start with an example. So this is section 15.3. I just got all these the notes for these up last night, so that's why I'm running slightly behind here. So 15.3 is double integrals in polar coordinates. So, as an example, I want you to think about this function. If I gave you something like the integral from, let's see, the double integral over d of the function x dA, so a volume integral of the function x, where d is the region where x goes between 0 and 1, and y goes between 0 and the square root of 1 minus x squared. So essentially what this is asking you is, there's your region D. What the function f of x and y is equal to x does is you can imagine that there's it's a plane that runs up in the x direction, and so this ends up with kind of like a weird cheese wedge. So it's all flat right here, and then it runs up in a plane like this, and then it has this edge that kind of curls back down along the edge back down to this point. So it's like this wedge with a circular arc cut on the outside of it. And I'm asking you to compute the volume of this. And the way that we would do it, based on our theory of double integrals, is we would say, okay, well, the way I've got this set up, it's a type 1 region. So for each particular value of x, I go from 0 to the square root of 1 minus x squared, and then the x values run from 0 to 1. So I should probably say that the double integral over d of x dA can be computed as the integral where x goes from 0 to 1 and y goes from 0 to the square root of 1 minus x squared of x dy dx. So we can sort of Fubini's theorem our way into this integral. And I look at that and I think, okay, well that's kind of ugly. I've got that square root of 1 minus x squared involved. And if I'm lucky, a u substitution will pop out when I'm done with this. In this case, it will. You do get an integral you can solve out the other side. But you can see that anytime you're integrating and you're throwing around pieces of circles like this, the integrals can get really nasty. Right? So the whole point of section 15.3 is that there are some domains that are much more natural to describe in polar coordinates than in rectangular coordinates. So when I look at this region D down here, I think, well, if I describe this in polar coordinates, this would be a rectangle in the sense that all of it would be described by constants. So in Cartesian coordinates, and I recognize this was last quarter, but you're supposed to remember, I suppose. So in Cartesian coordinates, we have the region where we go from y is equal to the square root of 1 minus x squared on the top, and y equals 0 on the bottom, and x between 0 and 1, whereas in polar coordinates, so I'm just going to rewrite this again, 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to the square root of 1 minus x squared. Whereas in polar coordinates, and that's mostly on the board. Make sure I cut myself off so this all stays on video here. I could describe the same region in terms of an r and a theta. So if I had a radius that I wanted to work with and a theta that I wanted to work with, how would I describe that region using r and theta, like in polar coordinates instead? It's a rectangle. What should the radius run between?
0.
Yeah, right? I mean, if you think about casting rays from the origin, the radius values start at 0 and end at 1. And the angles that I sweep between start at 0, and then you rotate around until you get to pi over 2. And so this is a rectangle in polar coordinates. We called this a polar rectangle when we were studying that chapter because it's defined by constants. Well, that would be nice. I would love it if I could do a double integral where instead of having functions inside of the limits of integrations, I just had constants. So that'd be cool if I could swap out that set of limits of integration with this set. After all, they describe the same region. The problem with doing it directly is a geometric one. So there's one more piece that we need in the picture in order to actually do this. So I don't have a ton of room to work with here. So when we took that region, the original region that we wrote down, and we made the move where we replaced dA, unit area, with dx dy or dy dx, what we were doing is we were cutting the region up into these little squares, right? We're decomposing the region into little rectangles, and each of the little rectangles I'm thinking of as being the area of it is dA, and I can think about dA as being dx times dy. They're rectangles. It doesn't matter where I move them. If I do an equidistant chop of this thing, so chop it up into equal pieces, all of the areas can be thought of as being a little change in x times a little change in y. Right? That is why we're allowed to do this when we take this integral and replace it with the iterated integral, is that dA, the unit area, is dy dx. If I want to cut things up with respect to polar coordinates, I have to do something different. So if I do a polar coordinate decomposition, then instead of cutting it up into little rectangles, I get figures that look like this. So each of those rays I think of as being d theta wide. So I'm cutting it up into little rays, and each of these rays is d theta wide. So I'm sort of spraying rays out from that origin to cut the region up into polar pieces. And then the other variable I have to cut with, according to this coordinate system, is, well, that's what cuts would look like with respect to theta. What do cuts look like with respect to r? Well, they're going to be cuts that kind of come through like this. So this distance right here, I think of as a little tiny change in r. So if I look at this picture and I think to myself, all right, well, what is dA? The thing that you should notice is, for a fixed d theta, down here you have little polar rectangle pieces that look like that, but on that same d theta, if I get further out, the areas are much bigger. So the area of this thing, the dA, which would be, hey, how big is this little piece that you've created? Hey, how big is this little piece that you created? It changes based on r. The further away that piece is from the origin, the bigger the dA unit looks. As I slide it away, it gets bigger. So what we want to cook up is a way of replacing dA with some expression in terms of dr and d theta, but it needs to account for the fact that as I move out from the origin, these get bigger. Okay, so I'm going to take one of these out, and I'm going to show how we think about drawing it. So if you imagine that you've got the origin, and I'll draw my little sort of dA unit out here. This is the thing I'm trying to find, is what an expression for dA is. And admittedly, I'm using d instead of delta. You can make this rigorous by thinking about little increments instead. So this is more an intuitive argument for what's happening than a formally rigorous one. What do I actually know in the picture? I know that d theta is supposed to be this little tiny change in angle down here. And this distance right here, from this point to this point, is supposed to be dr, a little tiny change in radius. So I would like to know the area of that, which means if dr and d theta were small enough, it would kind of look like a rectangle, right? Circles get really flat when you start pulling them in to be very small, right? Very thin in angle and very thin in change in radius. So if I want to imagine for a second that this was a rectangle, or model it as a rectangle to approximate the area, I need to know how long this side is. I want to be able to say dA is equal to dr times a something. So I'm going to pretend it's a rectangle because it's approximately a rectangle. And now I just need to know what that is. So now this is your ancient geometry is going to hopefully come to bear here. If I ask you the question, this question. I've got a circle, and I have an angle theta in radians in the middle, and I'm interested, in this radius r, and I want to know how long this part is on the outside of the circle. Is there a formula for that? R theta. This is why you use radians, is because it's the simplest possible version of the formula. There's no dividing by 180 or pi is running around, right? This length is r theta. So the angle down here is d theta, and the distance you are out here is r. That's the radius for how far you are out from the origin out to that line segment. So how long is it? Radius times angle. R d theta, approximately. And so what that means is if we treated this thing like a rectangle for a second, the area should be dr times r d theta. And that is the polar unit area, is what that's called. dA is r dr d theta. Polar incremental area, or infinitesimal area. So just to emphasize here, this is sort of one of the big parts of the polar, how to do integrals in polar coordinates is, I want to cut the surface up into these little figures, but I can't do it with rectangles. I have to use polar rectangles, and the area of polar rectangles changes depending on where they're located. And here, remember I told you at the beginning, these get bigger as you get further away. That's what the R is doing, is it's scaling the polar rectangle. So the further away you get, the bigger it gets. Of course, when we change things into polar coordinates, and now all of a sudden I've got an integral in terms of r and theta, if there happen to be x's and y's running around, I better get rid of those, because I can't integrate x and y with respect to r and theta. If only I had a convenient pile of identities I could use to get rid of x and y and put r's and thetas in instead. So if, for example, I happened to see an x, I could replace it with r cosine theta. And if I saw y, r sine theta. And if I saw an x, this is often a convenient one. If I saw an x squared plus y squared, r squared. Remember, x and y are r cosine theta and r sine theta. So x squared plus y squared, the r's would survive, but the cosines and sines would turn into a 1. Okay, so this set of identities and this change, where you take dA and replace it with r dr d theta, that is enough to convert a Cartesian double integral into a polar double integral. So let's look at what that looks like in our particular case. So that function that we started with. So I can show you kind of what the process looks like. Sorry. So I think we started with the integral from 0 to 1 of the integral from 0 to the square root of 1 minus x squared of the function x dy dx. And we noted that that original region that we were working on, where we're between y equals 0 and y is equal to the square root of 1 minus x squared, we could have equally well have thought of this as radius goes between 0 and 1, angle goes between 0 and pi over 2. So this integral is the same as the integral where angle goes from 0 to pi over 2, radius goes from 0 to 1. This thing right here, if I change coordinates from Cartesian to polar, is no longer dy dx. It is r dr d theta, because that's how you measure polar rectangle infinitesimal area. And the last thing we've got to get rid of is this x right here. But x is r cosine theta. And I don't know about you, but generally I would expect, if I was doing an integral, and I ended up with something like this, this is like a no-technique integral. It's two basic antiderivatives. There's no u substitution, it's over. I can use Fubini's theorem. I can integrate it in any order that I want because all of the limits of integration are constant. This is a much easier integral in general than this one is. So if we're going to finish it up, just keep working through the example here. If I do the internal integral, I'm going to integrate r squared with respect to r, so I get 1/3 of an r to the third evaluated from 0 to 1 of cosine of theta d theta, which I think is just 1/3. Think that's right? So I'm just, this is a regular, these are no different than integrating with x's and y's. Yep?
Oh, no.
Oh, it's stretched, okay. Okay, then if you integrate the cosine, you get 1/3 of the sine of theta evaluated from 0 to pi over 2, which is 1/3. That's the answer. So this is a no technique integral. This particular one, you could have done it the other way. So I could show you what it looks like in the other direction just to remind you how the u substitution would work. If I did this in the other direction, so I did it in standard coordinates, I would have the integral from 0 to 1 of x, y evaluated from y equals 0 to y is equal to the square root of 1 minus x squared dx, which is the integral from 0 to 1 of the square of x times 1 minus x squared dx. And we got lucky in this case that there's a u substitution here. It's easy to write. In fact, the next exercise we're going to do is an example where you do this and there is no u substitution. You can make no progress on the integral. So basically, as soon as people have to do this, where they're dealing with square roots as limits of integration, you should suspect that there's a polar coordinate transformation that working around. This is integrating underneath a circle. That's part of your suspicion that probably polar coordinates are at play. If you continued this, probably you'd have to say that this is u is equal to 1 minus x squared, so du is minus 2x dx, which means that minus 1/2 of a du is equal to x dx. And since it's a definite integral, you would probably want to write down that u of 0 is equal to 1, and u of 1 is equal to 0. Just convert your coordinates at the same time, because you don't really want to be going back and forth with these. And that would get you the integral from 0 to 1 of the integral from 1 to 0 of the square root of u times minus 1/2 du dx dy.
You already did that.
Yeah, it's dx. It's dx. Oh, it's not even a double integral anymore. It's this, right? Isn't that, yeah, we're, sorry, it's not a double integral. This is what we're down to. Oh man, but then I gotta integrate square roots. So minus 1/2 of u to the 3/2 divided by 3/2 evaluated from 1 to 0. Ugh. Still turns out to be 1/3 when you're finished, of course. But even in this really simple case, a lot more technique and a lot more nasty algebra go into solving it this way because of the square roots that show up. If you hate square roots, try polar coordinates. So I'll give you an example of a case where there is nothing to be done in the standard case. So this is kind of this works because textbooks like to give you exercises that force you into channels to practice things. Example 2. Calculate the double integral of e to the minus x squared minus y squared dA over the region D, where D is the region bounded by y is equal to the square root of 4 minus x squared and y is equal to 0. Blech. So there's all kind of problems with this. The first is, most obviously, okay, let's draw the region first. So this is the region of interest here, this stuff. That's D. Already your spidey sense should be going off. I bet there's a polar coordinate change happening here because I'm on a semicircular region. And that would let me chuck this square root thing. That is not the real issue in this question. The real issue is e to the minus x squared minus y squared has no elementary antiderivative. You're just stuck. It can't be integrated. That is a function that has no antiderivative. So the issue is that no matter what variable you start with here, the integral of e to the minus x squared dx has no elementary antiderivative. There is no function that you can write down in simple form that has e to the minus x squared as a derivative. It just can't be done. When we did series a billion years ago, at some point I had you integrate the series for e to the minus x squared because that's one of the only ways you can do it. You can approximate the function with its power series. So the function that has e to the minus x squared as its derivative is a power series. Has no formula, just a power series. So textbooks like to set problems like this up because it means there's just nothing you can do. And if you try to do this, integrating dx or dy, you're going to have to integrate e to the minus x squared or e to the minus y squared, and you can't. But since it's in chapter 15.3, which is called double integrals over polar coordinates, then you know it must be, by the logic of textbooks, that you're supposed to do a polar coordinate transformation to it. So, if we're going to do a logic of textbooks move here, the first thing I should do is I should rethink of the region D in polar coordinates instead of in Cartesian coordinates. So if I wanted to redescribe the region in terms of r and theta, what should I do? Be careful with your radius.
R is between 0 and 2.
Yeah, so positive radii. The temptation might be to go from -2 to 2, but that's going to end up getting you stuff you don't want when you start rotating. Think about radius in these cases as starting at the origin, from the origin out to the curve. Theta? 0 to pi. Okay. So now the only thing I've got left to do is there's this e to the minus. So the first conversion for this problem would look like the following. I can, instead of doing it in Cartesian coordinates, I could set this up as the integral from 0 to pi of the integral from 0 to 2 of e to the minus x squared minus y squared r dr d theta, because now I've committed to a version of dA in polar coordinates. And I have one last thing to do here, which is I've got these extra annoying x's and y's left over. Of course, I should be suspicious because x squared plus y squared is like a thing I know. So isn't this equal to, so this guy up here, minus x squared minus y squared is equal to minus x squared plus y squared, which is minus r squared. So notice what happened. Integral from 0 to 2, r e to the minus r squared dr d theta. I've taken a problem that couldn't be done because that function has no antiderivative, and I made a u substitution show up. So it went from an impossible problem into a basic problem. If you continue this problem, yeah, so I guess before I move on here, a lot of times what you do with a polar coordinate change is the extra factor of r that you pick up is really useful in a lot of contexts. Because you end up getting something that actually you can run a u substitution with respect to. And that's exactly what happens here. If I let u equal to r squared, then du is 2r dr. So 1/2 of a du is r dr. U of 0 is equal to 0. U of 2 is equal to 4. And you end up with the integral from 0 to pi. The integral that we did the u sub on is the internal integral here of the iterated pair. So now it's the integral from 0 to 4 of e to the minus u times 1/2 du. And that's integrated d theta. If you keep going, this becomes the integral from 0 to pi. The internal integral, when you integrate e to the minus u, you pick up a negative sign. So you get something like minus 1/2 of e to the minus 4 plus 1/2 d theta. Integrating this with respect to theta sticks a single theta into the equation that you put 0 and pi into, and so I think the final answer is 1/2 of e to the minus 4 plus 1/2 all times pi. Just working your way through the basics of how these integration goes. Yep.
Is there any like a formulaic way to like find the domain other than just like kind of looking at the graph?
Okay, so no. So generally, like I'll tell you what the general sort of shape of a pole. I can define what it means to take a little integral in the polar setup. So the one way to do it from the sort of like individual problem level is exactly like this. You write down the domain, you recognize that it looks nice in polar coordinates. You notice that you would get a really convenient substitution of variables if you performed it, and then you just do it, right? The more general setup for a polar integral is basically this. If you have a region, if your domain D has the form that looks like this, where you go from theta 1 to theta 2, and then you go, this is function on the outside of this wedge is defined as f is equal to, r, the radius is equal to f of theta. So now not a circle, but just some sort of general curve. And then the double integral of f dA over d is the integral from theta 1 to theta 2 of the integral from 0 to r of theta of f of r and theta, r dr d theta. So this is the sort of general setup. Looks like this. But no, generally there's no like, either I give you the region in polar form, or you have to discover it by looking at the shape and realizing like, oh, there's sort of radial function happening here. So I'll say in application what happens is a lot of areas of physics and engineering are just set up thinking radially anyway from the get-go, right? You just think like anytime you have radially symmetric fields, for example, you just come out the gate with polar coordinates. The other thing I'll say about polar coordinates is polar coordinates turn out to be the basis for 2 different coordinate systems in 3 variables. So it's really important to understand what's happening here in the polar setup because when we go to 3D, when we start doing triple integrals or 3-dimensional coordinate systems, one way of extending the polar coordinate system to 3 variables is to tack a z variable on. So you have coordinates in the polar plane and then a z variable that tells you your height. And that's called cylindrical coordinates. And the other way that you could do it is if you have a polar point, you could actually take it and rotate it with another angle. And those are called spherical coordinates. So either find an r and a theta in the plane and then lift straight up to get a z value, which is cylindrical, or figure out an angle and a radius and then rotate that up to get the third axis or the third coordinate, and that's spherical coordinates. So both of them are basically founded on understanding how polar coordinates work and thinking about things in polar coordinates. And shockingly common in applications. Amir?
So just to make sure, when you switch the variables, you don't have to do anything because it's already like 4 constants as the balance?
Yeah. Yeah, I can do, in this case, I can do r d theta in any order that I want, right? Because once you're on a polar rectangle, Fubini's theorem says, who cares what order you do it in? I will say in this setup, it actually does matter, because here, if r is a function of theta, right, this is like a type 1 region, basically, where I need to go between the 2 functions first. That'll introduce another variable of theta, and then, so if I just do the interior integral here, the r's will be gone, but there will be thetas running around all over the place. And then the external integral with the theta in it, that's what destroys everything. So generally in polar coordinates, we think of theta as the controlling variable, and r usually depends on theta. So dr, d theta is the typical way that we set this up. If we're on a rectangle, it doesn't matter, right? But like, yeah. Somebody had a hand up.
I was just going to ask, like, it's never that it's a function of r, right?
So that just doesn't happen. It's weird. Yeah, you could write theta as a function of r, but that would be like squiggly edges, and it's a weirder way of setting it up. And almost always when you're working in in application, you want to think about the angle as dictating radius because it's a more natural way of thinking in the coordinate system, right? Like not where you're at determines what angle you're at is a weirder way of doing it. You can, but it's not often done. Part of that is because since the polar coordinate system is built on sines and cosines, sine and cosine are not really invertible functions. They have really restricted domains on which they're invertible, and so it messes everything up. You have to break the problem up into pieces where the functions are defined, and it's a complete mess to do it that way. Okay, so now that we've learned the basics, and this is essentially the whole upshot of 15.3 is this kind of stuff, right? Look at a region, figure out how to write it in polar coordinates, change the limits of integration on the integral, and then just do the integral. I want to show you my favorite integral of all time ever. So, we already talked about this guy, e to the minus x squared dx. And I noted that doesn't have an elementary antiderivative, which is frickin' obnoxious because that function is basically the heart of all of statistics. So this is called the Gaussian function, or its more common name is the normal distribution. Or at least a normalized version of it. And if you've sat through a statistics class where you've had to calculate z-scores, you go to the back of the book and there's some table and you look up some numbers on the table to calculate a z-score, you were integrating that function. It didn't tell you that's what you were doing, but that's what you were doing. When you calculate a z-score at the back of your book in a statistics class, and it shows you the table that looks like this, and it says the area under the curve, and this is z right here, you integrated that function from minus infinity to z. It didn't tell you that, but that's what you were doing. You were integrating some normalized version of this from minus infinity up to z. If I want this actually to be a probability distribution, I need the area under the curve, the whole thing, to be 1. Which means, if I want statistics to work, I better know, so I need to know, what the integral from minus infinity to infinity of e to the minus x squared dx is. I need to know that. If I knew that, I could make all of this sort of z-score, normal distribution statistics work. So what I'm asking then is the following question. Given that I cannot calculate an elementary antiderivative of this, is there still a way, imagine I drew this symmetrically here, is there still a way that I could find the area from minus infinity to infinity of e to the minus x squared dx? Actually, I'm very, very curious. Sometimes people know the answer to this. Does anybody actually know?
Can you try improper integral?
Well, I'm going to, oh, you better believe there's an improper integral coming. I'm just curious if anybody actually knows the answer. It's weird. And not at all obvious.
I was at an integration game and I remember something with this.
Okay.
I didn't do it.
So we're going to say is whatever that value is, it's definitely a thing that exists because e to the minus x squared goes to 0 really fast. So I'm going to tell you up front, this is an improper integral that converges. All right, well, let's take a look at a slightly easier problem. What if I cut it in half? And I just did half of it. Well, then I would be looking at the integral from 0 to infinity of e to the minus x squared dx, just so I have one limit instead of two running around. And if I know half of it, I know the whole thing. It's symmetric, right? Okay, so here's what you do. That's not a solvable problem, so I'm going to square it. I mean, after all, if I can't solve this problem, I also can't solve the square of the problem. So I'm going to take e to the minus x squared dx, and I'm going to square that number. Whatever number it is, I'm going to square it. You might think, why on earth would you do that? Well, so I could write the trivial algebraic observation that if I square this thing, that's the same as writing this down. I mean, if I could figure out what the square of it was equal to, I could take the square root and that would tell me what the original function was, right? Why on earth would I do that? I've made the problem twice as bad. So if you've ever heard a professor say the word dummy variable ever, What it means is, does it actually matter what letter I integrate with respect to? I mean, this is a number. I could put a t here, or a z, or an omega, or a theta. Would it change the answer? No. So I'm going to conveniently choose the letter y. So if you disagree with me at any step, you let me know. So I don't think I've changed anything, because if I just dummy variable up a y, whatever number that is, it's still the same number. Okay, do you remember that if I have a constant times the integral of a function, I can just put the constant inside the integral or take it out? It doesn't matter. Constant inside, constant outside, it's a constant, right? This thing right here is a number. It's a number. So I'm going to put it inside the other integral. So now I've got the integral from 0 to infinity. That's that integral right there. And I'm going to stuff this thing inside. So now it's the integral from 0 to infinity of e to the minus x squared dx. See, it's a number, so I just jammed it inside the integral. Like e to the minus y squared dy. That's legal. It's just a constant. Interestingly, though, does that e to the minus y, is there an x inside that function right there? Oh, so it's constant with respect to this integral. It doesn't change with different values of x. It's e to the y, right? So it's for any fixed value of y, that's a constant. So I'm going to take that e to the minus y squared, I'm going to stick it inside that integral. Okay, so now we have the integral from, so I guess the trick I'm using now is I'm taking this thing, which is constant with respect to x, and I'm jamming it inside the other integral. E to the minus x squared, e to the minus y squared, dx, dy. And of course, two exponentials multiplied together, you add their powers. E to the minus x squared, minus y squared, dx, dy. Oh, that's starting to look tempting. We just did this integral, where when we change to polar coordinates, I can't solve this integral, but when we change to polar coordinates, an r popped out, so I could use a u substitution, right? I gotta deal with this crap. What does that mean? 0 to infinity, 0 to infinity. Let's take a look in a second for the domain we're actually integrating over. Now, I'm waving my hand slightly here. This can be made very tightly rigorous, but I'm trying to give you the idea without burying you in technical details. The domain that we're integrating over looks like this. X goes from 0 to infinity, and also y goes from 0 to infinity. Any combination of those is possible. So essentially what I'm doing is I'm integrating this surface, which is radially symmetric, over the first quadrant. Essentially what I'm doing is I'm calculating the volume underneath this surface sitting over the top of quadrant 1. One way of thinking about what that surface looks like is it looks like half of the normal distribution, but swept out in a circle. So it's kind of like a bell. It starts big in the middle and then sweeps out on the sides, like a cymbal on a drum kit. Okay. So one way of, now we all learned, because I sort of battered on about it in the earlier class, that when you have an improper integral, it's actually not really a thing, it's a limit, right? So what that limit represents, with the way we've written it down right now, is if we took a square that was, I don't know, c by c, and then I took the limit as c got bigger and bigger and bigger and bigger and bigger, I would eventually recover the volume underneath the whole quadrant, right? This is what this is telling you to do. So essentially, this integral is equal to the limit as c goes to infinity of the integral from 0 to c of the integral from 0 to c of e to the minus x squared minus y squared dx dy, and I can't do anything, even though I've got it reduced now to an integral without infinities in it. I still can't do anything because there's no antiderivatives. If I would like instead to think, if only I could get polar coordinates in here, the dx dy would become an r dr d theta, and that would be an r squared, and I could use u substitution. So here's the next big leap. Is there a way of describing this region involving a limit of a polar region instead of a rectangular region. How should I do it?
I mean, you could do radius goes to infinity.
Ah, okay. So, will you agree with me that if I set it up like this, and I let r go to infinity, doesn't that actually cover? Wouldn't that be the whole volume? If I just take the circle, instead of saying, oh, take a square and let the two sides of the square go out forever, that's the whole figure out to infinity. But I could do it radially too. If r goes to infinity, I'm just saying, well, just do it with the radius instead of x and y. Instead of letting a square get bigger, let a circle get bigger. It's the same thing as r goes to infinity. It's still the whole first quadrant. And that's the trick. This integral here is the limit as r goes to infinity of the integral from 0 to pi over 2 of the integral from 0 to r of e to the minus r squared r dr d theta. All right, we're deep in it now. So the reason that we did that, if I write down the integral from 0 to pi over 2 of the integral from 0 to r of e to the minus r squared r dr d theta, is now I have an obvious u substitution I can use. If u is equal to r squared, then du is 2r dr. U of 0 is equal to 0, and u of capital R is equal to r. I should limit here. So this is the limit as r goes to infinity of the integral from 0 to pi over 2 of e to the minus u times 1/2 du, and then you integrate d theta when you're done with that. Oh, and integrate it from 0 to r squared. Just u sub. I'm gonna just tell you what that evaluates to. 0 to pi over 2. Okay, so the integral of e to the minus u is minus e to the minus u. So if you put in the r squared, you're gonna get negative 1/2 e to the minus r squared. Plus 0 plugged into this gives you 1. This gives you 1/2 that pops out. All of that times the 1/2 that came from the du. Wait, no, I double counted the 1/2 there, haven't I? Yeah? Minus 1/2 e to the minus u. You put in the r squared, you get this. You put in the, then you subtract off this. When you put in 0, you get that. I think this is correct. Okay, well, there's no thetas in here, so if you integrate with respect to theta and then plug in the numbers, I think what you get is the limit as r goes to infinity of that same quantity, minus 1/2 e to the minus r squared plus 1/2 times pi over 2. What's that limit equal to? What happened? There's only one r in the whole thing. It's right here. E to the minus r squared as r goes to infinity. 0. So this entire thing is pi over 4. That's weird. So what have we actually found right now? What is that pi over 4? The pi over 4 is the volume of this surface under the first quadrant. Well, that's pretty weird. Okay, so what is the problem we've actually solved here? It's worth going back and thinking, like, what the hell did we do? Remember that this thing originally, all of that trick that we originally set up, this was equal to the integral from 0 to infinity of e to the minus x squared dx squared. All of the work that we did was in interpreting what that integral was, and what we found now is the integral from 0 to infinity of e to the minus x squared dx squared is pi over 4. Okay. So, doesn't that just finish the problem? All of that chicanery And if I take the square root of both sides, I get the integral from 0. This feels like cheating. Oh, but we only got half of what we wanted. We found this area, which was the integral from 0 to infinity. So what's the whole area? Root pi. That's freaking weird. Root pi? So if you've done a statistics class at a higher level and you've actually seen the fact that when you write the Gaussian distribution down, you do 1 over root pi in the setup, the reason is you're dividing out the area of the curve minus infinity to infinity of e to the minus x squared dx is the square root of pi, which is weird.
But the actual equation is 1 over square root of 2 pi.
So that's because they adjust it so that there's 2 normalizations that happen. The first is you divide out by the area under the, first you set it up so it's got mean 0 and variance 1. And then when you recalculate the function that you used to do that, then you find out the area is like 1 over root 2 pi or something like that. It's the same argument, but it's a slightly different version of the function e to the minus x squared.
Oh, okay.
Right? But you do it exactly the same way. Like this, I think this is a trick of Euler's actually. This like, I mean, again, to me, the reason I love this integral so much is because it's absurd. The idea of squaring the integral so that you can cook up a second variable and then jam them together so that you can use polar coordinates is like, it just seems like it comes from the moon or something, right? Like, and I believe the idea is originally due to Euler or somebody like him, these geniuses that were thinking about these things. Like, this is not an obvious move to make. I may actually ask this as like a bonus question on the final or something because it would make me laugh to do that. But it wouldn't be anything you're required to learn. You don't need to know this, right? But I will say that this kind of technique where you solve indefinite integrals in one setting by putting them into a different setting and making the math work, that is a common trick that shows up in a lot of areas. If you're interested in, like, it's not obvious to me why, when you're doing this, that root pi is a thing that should even come out of this. Where does the pi come from should be a question that you've got. There were no circles in what we wrote right here, right? The circles came in when we tricked it in with polar coordinates, but this function by itself has a power series that you could integrate, and the answer would still be root pi. So if you're interested in I think that 3 Blue 1 Brown actually has a video where he talks about this specific problem and why you might believe there's something more natural about the way the pi shows up. So if you want to nerd out on YouTube and watch the math, because everyone's got all the time in the world for that, right? Anyway, all right, so go work on your polar integrals. What I want you to do for Thursday is, and I'll post this, we're going to do center of mass, which is the big application of double and triple integrals, and that'll be 15.4 and a little bit of 15.6, which talks about triple integration. So, see you guys.